Alright, so on this video, we're going to do a quick review of chemical reactions from Chem 1, looking at the different types, how to balance, and how to predict products. So, information that you get from equations. Remember that reactants are on the left side of the arrow, products tend to be on the right side of the arrow. Some other things that you may note is the physical state of substances in the reaction. So these use the symbol after the formula for each substance. So each reactant, each product will have one of these. They use S for solid, L for liquid, G for gas, and then AQ for any solutions or substances in aqueous solution. You might also see any special conditions needed for the reaction to occur. These will actually be above the arrow. These will include if there is a catalyst present, the formula of the catalyst is written above the arrow. If heat is added to the reactants, it might have a delta H above the arrow. Or if the reaction needs to occur at a specific temperature or pressure, that will also be above the arrow. So looking at the different types of reactions, our first one we went over was synthesis, where we have two or more reactants and they combine to produce one product. An example is magnesium plus chlorine gas producing magnesium chloride. Multiple reactants, a single product. The opposite of that is decomposition, where we have a single reactant that is split up into multiple products, and these could be split up into elements if it's a binary compound, or it can be split up into different compounds. So an example is this one. We have sodium hydrogen carbonate. Whenever it decomposes, breaks up into sodium carbonate, water, and carbon dioxide. And I'm going to kind of skip down from our order from Chem 1 and go ahead to combustion reactions. Combustion reactions have oxygen as a reactant. Most of the times we think of true combustion reactions where we have a hydrocarbon plus oxygen producing carbon dioxide and water. So here we have methane and oxygen producing carbon dioxide and water. You may also see reactions that still have oxygen as a reactant, but do not have a hydrocarbon. These can still be classified as combustion, but they are not going to produce carbon dioxide and water. So this one, we have potassium and oxygen. When they react, they will produce potassium oxide. So it is actually both classified as synthesis and combustion because oxygen was a reactant. On to single replacement. So with single replacement reactions, we have an element and a compound on the reactant side and the product side of the equation. And the element by itself is trying to replace the equivalent ion in the compound. So if it's a metal or something that would produce a positive ion, it is trying to replace the positive ion in the compound. If it would normally be a negative ion, it is trying to replace the negative ion in the compound. So here's an example, one that we performed in Chem 1 a couple of times. We have silver nitrate and copper, and it will produce silver and copper 2 nitrate. With double replacement reactions, we actually have two compounds on both sides of the equation on the reactants and products, and the positive and negative ions interchange, so everyone switches partners. So I tend to switch my positive ions, that way they are not with their beginning negative ions. And do remember that your two positive ions do not go together and your two negative ions do not go together. So looking at this one, we have potassium fluoride and calcium sulfide. Our two positive ions are the potassium and calcium if they switch places. The potassium now pairs up with the sulfide to make potassium sulfide, and the calcium now pairs up with the fluorine to make calcium fluoride. Alright, so I want you to check out this quick video. It's the 5 types of reactions off of YouTube. It just shows you a little bit of a diagram with them as well. All right, so I want you to try a couple. So I have 5 on this slide and then 6 through 10 on another. These are in your lecture notes if you have them printed out. Feel free to pause the video, take a moment, try to classify these as one type of reaction, and then try to balance these. Remember, when we're balancing an equation, you want to make sure that you have the same number of atoms on one side as you do on another. So feel free to pause and work through these 5. And here's the answers to them. So the first equation, you have 2 substances that are combining into one. So it could be a synthesis. Here, because oxygen is a reactant, you could technically say it is combustion, but that's very unlikely for this one. And then balancing it, you would need 8 sulfurs on the right to match the 8 on the left. And then you would need 12 oxygens to match what you have on the other side with the 24 oxygens. In our second one, we have hydrogen combining with oxygen to produce water. So this is a synthesis because they are combining to produce one substance. It's also a combustion because oxygen is a reactant, and this does have that hydrogen even though it doesn't have carbon combined. The third one is the single replacement reaction. We have solid zinc and hydrochloric acid, so an element and a compound, and they're going to produce the zinc chloride and hydrogen gas. So the 2 metal ions, the zinc and the positive hydrogen, switch places. The fourth one is a decomposition reaction. You have a single reactant and multiple products. Number 5 is a true combustion reaction. You have a hydrocarbon plus oxygen producing carbon dioxide and water. So here's the next ones. Feel free to take a moment, pause the video, and walk through these, classify what type of reaction they are, and balance them. Number 6 is a double replacement reaction. We have 2 compounds on the reactants and 2 compounds on the products, with those positive ions switching places. So we have silver nitrate and zinc chloride. When they switch places, they're going to produce silver chloride and zinc nitrate. Number 7 is a synthesis reaction. We have nitrogen plus hydrogen producing ammonia. So multiple reactants, a single product. Number 8 is a decomposition reaction. We have hydrogen peroxide splitting into water and oxygen. So one reactant, multiple products. Number 9 is a synthesis yet again. We have iron with chlorine gas producing iron 3 chloride. We have multiple reactants and a single product. And number 10 is a double replacement reaction. We have 2 compounds producing 2 compounds. So we have the iron 3 sulfate and potassium hydroxide. The positive ions switch places to produce potassium sulfate and iron 3 hydroxide. So some things to remember from Chem 1. Single replacement reactions do not always occur. These can be no reaction. In order to determine if the reaction occurs, we are going to look at the activity series of metals and halogens. So with our activity series, it is going to list metals in order of decreasing reactivity. So the most reactive is at the top, least reactive is at the bottom. A reaction will occur when the free metal, the element by itself, is more reactive than the metal currently in the compound. So it has to be more reactive in order to replace it and boot it out of the compound. So here's an example. If we have aluminum and copper chloride, aluminum is higher on our activity series than copper. So aluminum can replace copper in the compound to produce the aluminum chloride and copper solid. And we also use this with halogens. So for halogens, reactivity decreases down the column. So if you look at their location on the periodic table, fluorine is going to be most reactive, iodine would be least reactive. Now, if you have not noticed, there is not an activity series on your reference sheet. So your general order that you're going to follow for metals, all representative metals are going to come before transition metals. So if you have a representative metal and a transition metal, the representative metal will always win. The general order for metals is group 1 metals are the most reactive. Group 2 is the most reactive, followed by aluminum. Then it is going to be the row 3 transition metals, then the row 4 transition metals, then the row 5 transition metals. You should be able to use this general trend to match up what would come next. The only true exception is that copper is extremely low on the list, even though it's in the first row of transition metals. It is very, very close to the bottom. So copper generally does not replace other metals. So feel free to pause the video if you feel comfortable with single replacement. I'm going to walk through these of can they replace or can they not. So the first one, we have aluminum and silver chloride. Aluminum is a group 3 metal, silver is a transition metal. So this should occur. So the aluminum is switching places with the silver. So the silver will come out by itself and the aluminum will pair up with the chlorine. Do make sure to crisscross your charges. So aluminum's a +3, chlorine's a -1, so it's AlCl3. And from here, you could balance it. You can also add in your state symbols, which we'll talk about in a little bit. So balancing, we have 3 chlorines on our product side, so we need 3 on our reactant side. That gives us 3 silvers on the reactant side, so we need 3 on the product side. Looking at the second one, we have silver and magnesium chlorate. Now, silver is a transition metal, magnesium is a group 2 metal. So silver should not be more reactive, so this can be no reaction. The third one, we have potassium iodide and chlorine. Now, since chlorine is a halogen, it is trying to replace the halogen in the compound, so the iodine. Chlorine is above iodine on the periodic table, so these will switch to produce the potassium chloride and iodine, remembering that it's diatomic. And then from there, you could balance it by making 2 iodines on the reactant side and 2 chlorines on the product side. And that also matches up your potassiums at the same time. With our last one, we have copper nitrate, copper 1 nitrate, and calcium. Calcium is a group 2 metal. Copper is a transition metal, very low on the list. So these will switch. So calcium pairs up with nitrate. Remember to crisscross your charges. And copper is going to come out by itself. And then from there, you could balance it. We have 2 nitrates on the product side, so we need 2 on our reactant side. That gives us 2 coppers, so we need 2 coppers on our product side as well. All right, switching over to the double replacement reactions or double displacement reactions, whichever ones you see. These tend to occur between compounds in aqueous solution. And remember, aqueous solution means the material has been dissolved in water. So these are what most of our reactions we perform in AP Chem are. So remember, a solution is a homogeneous mixture where a solute is dissolved in a solvent. So most of the time, we have water dissolving another substance. So remember, solutes are the dissolved particles in the solution. So what is being dissolved? The solvent is the dissolving medium in a solution. So in all of our aqueous solutions, that is going to be water. And here's actually what it would kind of look like. So we have our solute, our blue crystals. Our solvent is our water. And when they combine, it is now going to make this dissolved liquid, so this solution. which is actually blue in color, but mostly water. So all of the particles have been dissolved and distributed in between all the water particles. So whenever we're going through a double replacement reaction, you're going to notice one of several things that are going to occur. It will either form a precipitate. So remember, precipitate is a solid, so a lot of times we have a solid that settles at the bottom. It could produce a gas, something like hydrogen sulfide gas, or it could make a molecular compound like water or sulfur dioxide or something of that sort. One thing to know, since we mentioned precipitates, if a precipitate forms, remember that means it is not soluble, so it becomes a solid. Looking at your solubility rules, remember if something is soluble, it is going to dissolve in water. So it has that physical state of aqueous or aqueous. If something is insoluble, it will not dissolve in water. So it is going to precipitate, and it has the designation of S for solid. You must memorize your solubility rules from your memorization sheet. We're going to use these a lot, and these are not provided on the AP exam. The only way to find and label a precipitate in a double replacement reaction is to know your solubility rules by heart, particularly ones for ammonia and nitrate. Those can help you with most problems. So let's actually try some double replacement reactions. We're going to predict the products of the following reactions, balance them, and label the products as soluble or insoluble. So we're going to give them an aqueous or a solid designation. So on this first one, we have aluminum sulfate and potassium hydroxide. If you look at your solubility rules, both of these are going to be aqueous. So we are truly starting with two aqueous solutions. Double replacement, when they switch partners, the aluminum and the potassium are positive, so they will switch. So aluminum will now pair up with hydroxide, and remember to crisscross your charges. Potassium will now pair up with sulfate, and yet again, crisscross your charges. So we predicted our products, balancing it. See, we have three sulfates on our reactant side, so we need 3 on our product side. That gives us 6 potassiums on the products, so we need 6 on our reactants. That gives us 6 hydroxides, so we need 6 on the product side, so we would actually multiply that by 2. And that gives us 2 aluminums and 2 aluminums. So it's now balanced. Then we need to label the products as soluble or insoluble. So if you look up the rule for hydroxides, or if you have it memorized, hydroxides are insoluble, except group 1 strontium, barium, and ammonium. So the general is except for group 1. So this is actually going to be a solid, so that's going to be our precipitate. And potassium sulfate, sulfates are soluble, and generally all group 1 salts are soluble. So this is going to be an aqueous solution. Let's look at the next one. And feel free to pause the video and try these on your own, and then come back and check your answer. And we're going to do the same process as the last one. So our first one, we have nickel 2 nitrate and potassium sulfide. All nitrates are soluble, and potassium sulfide is a group 1 salt, so it's also soluble. When these switch places, potassium is going to pair up with the nitrate. The nickel 2 is going to pair up with sulfide. So they crisscross charges. Balancing it, we have 2 nitrates on the left, so we need 2 on the right. That gives us 2 potassiums. We already have 2 potassiums on the other side, and we have 1 nickel on both sides. So that is actually balanced. So our state symbols, so remember all nitrates are aqueous, so are all group 1 salts. Sulfides are insoluble, so solid, unless it's group 1, 2, or ammonium. So this is going to be our precipitate in that case. For the last one, we have potassium phosphate and barium chloride. Both of these are going to be aqueous. When they switch places, the positive potassium and positive barium are switching out. So potassium is going to pair up with chlorine to make potassium chloride, and that is a +1 and -1, so there's no subscripts. Barium is going to pair up with phosphate. So remember, phosphate has a charge of -3. Barium has a charge of +2. Balancing wise, so we have 2 phosphates on the right, so we need 2 on the left. That gives us 6 potassiums, so we need 6 potassiums on the right. That gives us 6 chlorines, so we need 6 chlorines. That gives us 3 bariums and 3 bariums. All right, so potassium chloride. Chlorides are soluble except silver, lead, and mercury. And all group 1 salts are soluble, so this is aqueous. Phosphates are actually insoluble except for group 1 and ammonium. Oh, excuse me, I spoke and said that they're insoluble, so they are solid. All right, another type of double replacement reaction you'll actually come across is an acid-base neutralization. It's just a double replacement reaction, but your 2 reactants are an acid and a base. So remember, when you combine an acid and a base, it's going to produce an ionic salt and water. So remember, acids tend to start with H+, those hydrogen ions. Will also, in Bronsted-Lowry form, it will actually donate hydrogen ions to another substance in the reaction. Bases, if we use our Arrhenius definition, usually end in OH, so in that hydroxide. However, with Bronsted-Lowry, those bases can actually accept hydrogen ions from the other substance in the reaction. And what we mean by a salt, the one exception is ammonia. So ammonia is actually one of our Bronsted-Lowry bases that comes up fairly common. And salts are going to be any ionic compound that is not an acid or a base. So it should not be an acid or base that's being produced in this case. So let's look at these. We have hydrochloric acid and magnesium hydroxide. If these perform a double replacement reaction, remember our 2 positive ions are switching places. When that occurs, the H pairs up with the OH to make water. And then the magnesium pairs up with the chlorine to make magnesium chloride. And then from there, we could balance it. So we have 2 chlorines on the right, so we need 2 on the left. That gives us a total of 4 hydrogens on our reactant side, so we need 4 on our product side. If you're adding the state symbols on here, remember water is a liquid. It is not aqueous solution. It is just a liquid by itself, but the magnesium chloride would be aqueous. So this does not form a precipitate, but it does produce that molecular compound, the water. Looking at the second one, we have sulfuric acid and sodium hydroxide. When these combine, the hydrogen and the hydroxide combine to make water. And then our sodium is going to pair up with our sulfate. To balance this, we need 2 sodiums on the left. That gives us a total of 4 hydrogens on the left, so we need 4 on the right. Adding our state symbols, remember water is a liquid. Sodium sulfate would actually be an aqueous solution. Now, touch and base, since we mentioned Bronsted-Lowry acids and bases. So remember we said acids are going to donate hydrogens, bases are going to accept hydrogens. Those are going to become our conjugate acid and conjugate base on our product side. This is going to include more acids and bases. So water can be considered an acid and a base. It actually includes more bases overall because they do not have to have hydroxide to be a base. This will also include some of our weak acids and weak bases as well. So our conjugate acid is going to be our particle formed from the base after it accepts that hydrogen. So the base is accepting that hydrogen to become the conjugate acid. The conjugate base is the particle remaining after the acid donates that hydrogen. So the acid gives up a hydrogen to become the conjugate base. So let's look at this example. And we're just going to label acid base, conjugate base. So we have ammonia and water producing ammonium and hydroxide. So I always look and see what two things pair together. So ammonium and ammonia are closely related. Water and hydroxide are closely related. So you want to see what happened to the ammonia from the reactant side to the product side. It went from being NH3 to NH4+. So it added a hydrogen or accepted a hydrogen. So this is our base and it becomes our conjugate acid. With the water and hydroxide, water went from having 2 hydrogens to having 1. So it donated a hydrogen. So it's our acid and it becomes our conjugate base. Let's look at one more example. This one, we have nitric acid and water producing nitrate and the hydronium ion. Remember, H3O plus is the hydrogen attached to water to make hydronium. So here, our nitric acid and nitrate are closely related, and our water and hydronium are closely related. So from nitric acid to nitrate, it lost a hydrogen. So nitric acid is our acid, and it becomes our conjugate base. Water went from being water to hydronium, so it added a hydrogen, making water our base and hydronium our conjugate acid.